Ohm's law describes the relation between the voltage difference across a resistor and the current through the resistor. It says that V equals I times R, where V is the voltage, I is the current, and R is the resistance. The SI unit for voltage is volts, for current is ampere, and for resistance is ohm. Let's figure out how a graph of the voltage versus current looks like. The voltage is on the y-axis, so this stands for the y. The current is on the x-axis, so I stands for the x. And the resistance is a constant value, independent of the voltage and the current for ohmic resistance. So it is a constant. Some resistors are non-ohmic. In other words, the value of the resistance changes with voltage or with current. For our purpose, we will study ohmic resistors only. So in the case of ohmic resistors, the resistance value is constant. So this brings us to y equals x times a constant, which reminds us with the equation of a straight line, y equals slope times x, where the slope is the constant of the relation. So a graph of voltage versus current should be a straight line passing through the origin, and the slope of the line should be equal to the resistance. For resistors in series, the current through the circuit is the same as the current through R1 and the same as the current through R2. However, if you measure the total voltage across the two resistors, you will find that it is equal to V1 plus V2. This information can be used to find out that the total resistance in series is equal to the sum R1 plus R2. For resistors in parallel, the voltage across the two resistors is the same, and in this simple circuit it is equal to the voltage of the battery. However, if you measure the currents, you will find out that the total current is equal to I1 plus I2, which makes sense because the current splits between R1 and R2. This information can be used to find the relation of the total resistance in parallel. In our experiment, we will plot a graph of V versus I for the resistor R1 in the beginning, and then we will repeat the same process for R2 and the combination of R1 and R2 in series, and then for the combination of R1 and R2 in parallel. After we obtain all of our data, we will plot a graph of V versus I that contains all four lines. Be sure to identify which line corresponds to which resistor or combination, and how much each slope is. In part 2 of the experiment, you will measure the total voltage across the two resistors R1 and R2 by using the built-in voltage current sensor. You will measure the voltage V1 using a voltage sensor, and then you will move the voltage sensor to measure V2. Then you will compare the total voltage obtained from the built-in voltage current sensor to V1 plus V2. The equation that we see here can be used to find the theoretical value of the total voltage. The total voltage obtained from the voltage sensor, V total in the graph, is the experimental value. So you will compare the two values. For two resistors in parallel, you will measure the current through each resistor and the total current in the circuit by inserting your ammeters as shown. Note that in order to connect the ammeter, it should be connected in series. In other words, you should remove a connection and replace it with the ammeter. Take a look again. So here is the original circuit. Remove some connections and insert the ammeters. Now in your experiment, you will use the current sensor to measure I1, and then you will move it to measure I2, and you will use the built-in voltage current sensor to measure the total current in the circuit. After this, you will compare this total current to the theoretical value of I1 plus I2. To set up the program for this experiment, we will start by clicking on Hardware Setup. And notice that we have the voltage sensor connected to channel A. So I'm going to click on channel A and choose voltage sensor. And here we can type V, voltage sensor shows up. And then also remember that we are using the built-in voltage current sensor to measure the current through the circuit. So I'm going to click on output 1 and click voltage current sensor. And this is all what we need for the hardware setup. Notice that most importantly, you had added all the sensors that you are using for this experiment. Next, we'll move to the signal generator because we are using the power supply side of the interface. So here, let's choose a positive ramp for the waveform. And let's choose a frequency of 1 Hertz and an amplitude of 2 volts. This means that we have a signal that starts at 0, increases up to 2 volts, and then repeats again. Okay. Now here I'm going to choose automatic. When you click on the automatic, this means that when you start recording, the power supply turns on automatically. And when you stop recording, the power supply turns off automatically without the need to coming back to this menu. Now, done with the signal generator, so I'm going to click here again to hide the menu. Next, we need to add a graph to show the results of the voltage versus current measurements. So I'm going to click on select measurement for the y-axis and set this to measure voltage. And notice that we have here voltage channel A corresponding to the sensor connected to channel A of the interface. Click on that. And here, instead of time, we need the current. And here we have the output current sensor, which remember is built in with channel 1, which is output number 1 of the interface. Now, if I click on record, the waveform repeats and repeats until I click stop. Now, there is a way to set up the program to collect data only for a certain period of time. So you can click on recording conditions. The start condition is when I click the record, so there is no need to change it. The stop condition, I want it to stop after 1 second. So the condition type, since we are talking about time, is time-based. And the recording time, I want this to be only 1 second. And then click OK. Then if I click on record, notice that this stored run will disappear and we have the new run. And it runs for only 1 second exactly. Okay. Now notice here that this is the second run, and here we have run number 2 displayed. To switch between runs, you can do this by clicking on this arrow here, and you can switch between run 1 and run 2. Okay. Now let's say that your graph looks like this, and you want your graph to be displayed on all of the screen. You can do this by clicking the auto scale button right here. This will display your graph on
all or most of the screen. Next, we need to add a linear fit because we want to find the slope of this graph. Now, to add a linear fit, you click on this button right here, the arrow, and then choose linear. If you have any other relation, you can choose the corresponding relation. But in our case, we have linear relation, y equals m times slope or slope times x plus an intercept. And here it added the line which looks perfect according to our data, and it shows you the slope as well as the intercept. Of course, we expect the intercept to be 0 in this case. However, due to some errors that you will have to talk about, we have just a small, very, very small y-intercept. Okay, the slope is 4.97, which represents the resistance of our circuit. Now, for the other trials, you can change the resistor and press the record again. Notice that the run will be stored. Okay, so I'm going to repeat the experiment for the other resistor, which is a 10 ohm resistor. So I replaced the resistors, and now I'm going to click record again. And here we have a slope of 9.95, which is very, very close to 10 ohms. Okay, again, you can click here on the auto scale if you want to see your graph on most of the screen. Next, let's connect the two resistors in series. Now we have the two resistors connected in series. So I will click record. And here is the new slope. And finally, we will connect the same two resistors in parallel and repeat the experiment. Now the two resistors are connected in parallel. So I'm going to repeat. Record again. Now, after this, I want all four graphs to appear on the same sheet. Okay. So to do this, I'm going to activate the multi-run button right here. Click on the button itself, and then choose the runs that I want to be displayed together at the same time. And notice that we don't care too much about this negative side, so I'm going to move the origin here, and then we can expand each axis individually, and notice that this is another feature that you can use. Now also we need all of these linear fits to appear everyone beside the line that it corresponds to. So this corresponds to this one, and this one is for this line, and so on. So you just sort them out correctly. Make sure everything is sorted correctly and nothing is switched. And then you can print out your graph. For part 2 of Ohm's law experiment, we need to set up the program to have two voltage sensors, one on channel A and the other one on channel B. As well as a voltage sensor for the output. For the signal generator, we need to set this to a DC with a voltage of 2 volts. And again, set it to automatic. Now for the display, we will need 3 digital displays to display the voltage of each of the 3 sensors that we are using. One for channel A, the other one for channel B, and the third one for the output voltage. For the recording conditions, we'll set it to 1 second as before. So the stop condition, it should stop time-based after 1 second. Now the same thing will be repeated for two resistors in parallel, but in this case we will be measuring current instead of voltage. So I'm going to go to hardware and remove these voltage sensors. Click on each one and then press delete. And replace them with current sensors. Here is a current sensor. There's another one. And for this one, again, we will use the built-in one. Notice how the voltage disappeared from here because we deleted the sensors. Now we have to select measurement and add the current sensors. So this is the one for channel A, this is the one for channel B, and this is the one for the output. But notice that I have to select the output current, not the output voltage. Now I will connect the circuit and start the program again.